Please pause the video and try this problem. Now let's discuss. We can number the carbons. This is a solvent that I don't expect to participate in this reaction, so I won't bother numbering this carbon. We can look for ionic bonds. This sodium here shows us an ionic bond between the sodium and the bromine. So we can assign roles. We expect the negative bromine to be the nucleophile. And what about the leaving group? Well, we know that a neutral chlorine can be a leaving group. What about this fluorine? Could we use the fluorine as a leaving group? Well, remember, start by looking at the formal charge. This is a neutral fluorine. Do we expect we could use this neutral fluorine as a leaving group? Well, previously in this video series, we learned that neutral chlorine, bromine, and iodine and neutral sulfonates in alkyl sulfonates are good leaving groups. And we learned that other neutral atoms are usually not acceptable leaving groups. So your general policy should be that you should generally assume that a neutral atom is not an acceptable leaving group unless you've specifically learned that it is an acceptable leaving group, or unless there's some clear reason why it should be an acceptable leaving group. If a neutral atom is not on this list, we will usually assume that it's not an acceptable leaving group. So that answers our question. We should assume that neutral fluorine is not an acceptable leaving group. We'll assume that neutral fluorine is not an acceptable leaving group because we haven't specifically learned that it is a good leaving group. That answers our question. We can see that fluorine is in the same column of the periodic table as chlorine, bromine, and iodide. Nevertheless, neutral chlorine, bromine, and iodide are good leaving groups, and neutral fluorine is not a good leaving group. We haven't really explained why that is. In a later video in this series, we will give an explanation for why chlorine, bromine, and iodide are good leaving groups, while fluorine is not. Since the chlorine is the leaving group rather than the fluorine, we will treat carbon 3 as the alpha carbon rather than carbon 2. Carbon 3 has a delta positive because it's attached to the chlorine, so carbon 3 can be used as an electrophile. Of course, carbon 2 also has a delta positive, but we're not going to treat carbon 2 as the electrophile because it's not attached to a good leaving group. Now we have to choose our mechanism. Carbon 3 is a secondary alpha carbon because carbon 3 is attached to two other carbon chains. Carbon chain here and a carbon chain here. So we're in the middle row of our table. Br- is our nucleophile in the middle column, so we predict an SN2 reaction. Now we'll draw our mechanism, and now we'll draw the product. Keep numbering the carbons in the product. This arrow tells us to draw a bond between the bromine and carbon 3. Now, the chlorine here is in front of the page. Remember that the nucleophile has to attack from the side opposite the leaving group. So the nucleophile will attack from behind the page, so the bromine will end up on a dash. If you don't draw the bromine on a dash, you'll get the problem wrong. Now, what about the hydrogen? Well, you cannot draw the hydrogen on a dash. As the bromine comes in from behind the page, it's going to push the hydrogen out of the way. It'll push the hydrogen in front of the page. So the hydrogen ends up on a wedge. The hydrogen is pushed by the bromine from behind the page to in front of the page. That's the inversion of configuration at the alpha carbon, which we expect for an SN2 reaction. If you draw the hydrogen on a solid line, that's wrong. This is a tetrahedral carbon. A tetrahedral carbon can't have three solid bonds. It should have two solid bonds, a wedge, and a dash. Now, you could just leave the hydrogen out completely. You could just treat this as a hidden hydrogen and leave it out completely. But if you want to draw the hydrogen, it has to be drawn on a wedge. How about at carbon 2? Carbon 2 is also a stereocenter. Should we invert the configuration at carbon 2? No, because carbon 2 did not participate in the reaction. Since carbon 2 did not participate in the reaction, there should be no change in the configuration at carbon 2. If you change the wedge for the fluorine to a dash, that would be a mistake. This arrow tells us to break the bond between carbon 3 and the chlorine. And it also tells us to change the charge on the chlorine from neutral to negative. Here's the product that the professor probably cares about as your answer for the problem. Remember that an alcohol is a solvent which you could use as a nucleophile. But because alcohol is a poor nucleophile, we're not going to use the alcohol in this case because there's something better. We would only use the alcohol as the nucleophile if there was no better nucleophile. Br- is a better nucleophile than the alcohol, so we won't use the solvent as the nucleophile. We used the Br-. We had to decide who we were going to use as our alpha carbon, carbon 2 or carbon 3. Carbon 2 is not attached to a good leaving group. Neutral fluorine is not a good leaving group, so we didn't use carbon 2 as the alpha carbon. Carbon 3 is attached to a good leaving group. Neutral chlorine is a good leaving group, so we did use carbon 3 as the alpha carbon. Remember that we've learned that neutral chlorine, bromine, iodide, and neutral sulfonates are good leaving groups. And if a neutral atom is not on this list, you should usually assume that it's probably not an acceptable leaving group. Now, later in the class, you will learn other neutral leaving groups that are acceptable leaving groups that you can add to this list. But the point is that neutral atoms that are not on this list are usually not acceptable leaving groups, unless you've specifically learned otherwise. Please pause the video and try this problem. Now we'll discuss. We can start by numbering each of the carbons, including this carbon. We don't need to look for ionic bonds because the ionic bond is already shown for us. They've already drawn in the formal charges for this ionic bond, so now we can identify roles. We start by focusing on atoms with formal charges. Because the sulfur has a negative charge, we expect that sulfur to be the nucleophilic atom. Now, who are we going to use as our leaving group? Well, here's a neutral chlorine. We would expect to use neutral chlorine as our leaving group. How about this alcohol? Could we use the alcohol as a leaving group? Well, no. This is a neutral alcohol. And remember that neutral groups are generally not good leaving groups unless we've specifically learned otherwise. We certainly haven't specifically learned that alcohols are good leaving groups. In fact, in a previous video, we actually specifically mentioned that alcohols are not good leaving groups. So we're not going to use this alcohol as our leaving group. We'll use the neutral chlorine. So we're not going to use carbon 4 as the alpha carbon. We're going to use carbon 1 as the alpha carbon. Carbon 1 has a delta positive, which will make it electrophilic. Carbon 4 also has a delta positive since it's bonded to the oxygen, but we're not going to use carbon 4 as the electrophile because it's not bonded to an acceptable leaving group. Now we can choose our mechanism. This carbon, alpha carbon, is a primary alpha carbon. That puts us in the top row of our table, and we decided our nucleophile is S- in the middle column of our table. The mechanism is SN2. Remember, don't assume that these reactions are SN2. Obviously, almost all the reactions we're covering now are SN2 because the purpose of this video series is to cover SN2. On your exams, SN2 reactions will be all mixed up with other reactions like SN1, E1, and E2. So at this point, you should always be using the table to determine the mechanism. If possible, it would be nice if you can work with this table from memory. Okay, so now we can draw our mechanism. The arrows will go from the nucleophile to the alpha carbon. So now we draw the product. This arrow tells us to draw a bond between the sulfur and carbon 1. And it also tells us to change the charge on the sulfur from negative to neutral. So the sulfur will no longer be ionically bonded to the sodium because the sulfur has lost its formal charge. We don't need to draw this spectator sodium ion at all. The sulfur should still be bonded to carbon 5 because the bond with carbon 5 was covalent. The sulfur is still bonded to carbon 5 in a covalent bond. If you leave out this carbon 5 in the product, that would be a mistake. This arrow tells us to break the bond with the chlorine and also to change the charge on the chlorine. Here's the product that the professor would probably care about on this problem. I hope you're still in the habit of numbering all the carbons. Why is it helpful to number all the carbons? Well, for one thing, if you don't number all the carbons, you could easily accidentally add or drop a carbon. This answer is wrong because I've accidentally added a carbon, but I might not notice that if I don't number the carbons. This answer is wrong because I've accidentally dropped a carbon, but I might not realize that if I haven't numbered all the carbons. We had to decide between using the chlorine as the leaving group and the OH. The neutral OH group is not an acceptable leaving group at all. So there's no question that we should use the chlorine as our leaving group. So we could not have done an SN2 reaction at carbon 4. I think there's a little bit of a trap on this problem because the alcohol group is written close to the nucleophile and the chlorine is written far from the nucleophile. Perhaps that was intended to trick some students into trying to do the reaction at carbon 4 rather than at carbon 1, so I hope you didn't fall for that trick. Pause the video and try this review quiz. Now here's the answers. When you defined these terms, I hope you gave two-part definitions. Each of your definitions should have had one part that refers to whether the role donates or receives electrons. And then there should have been a second part of the definition as well, such as this part, and this part. These are the best definitions for a beginner to learn for these roles. And then how do we explain the origin of the term electrophile? Well, as I discussed in an earlier video, the suffix phile means liker or lover. So an electrophile is an electron lover. Well, that makes sense. Electrophiles want to receive electrons. So it would make sense to think of an electrophile as something that likes or loves receiving electrons. So in this example we completed, carbon 1 was the electrophile and carbon 1 was receiving electrons, indicating that it likes or loves electrons. Now, how about this term nucleophile? How do we justify that term? That's a little less obvious. But nucleo refers to an atomic nucleus, and the key thing is the charge of a nucleus. A nucleus would have a positive charge. So when we say something's a nucleophile, what we really mean is that it's a positive lover. Nucleus lover here really means positive lover, because the charge on a nucleus would be positive. A nucleophile is something that likes to react with something that is positive. It should make sense that if you want to donate electrons, it's going to be easy to donate electrons to something that is positive. So a nucleophile likes reacting with something that is positive. Now, in this video series, we have not been looking in this video series at reactions where the nucleophile reacts with something with a positive formal charge, but we have seen in this video series that the nucleophiles that we've been focusing on have been reacting with things with a delta positive charge. The electrophiles that we've seen in this series have been electrophiles with a delta positive charge, like in this example. So here, this nucleophile was reacting with something with a delta positive charge, confirming that it likes to react with things that are positive. It's easier to donate electrons to something that has a positive charge, even if it's only a delta positive charge. And later you'll see many other reactions where nucleophiles react with carbons that have positive formal charges. So a nucleophile is called that because a nucleus has a positive charge. This term really means something that likes or loves to react with things with positive formal charges, or as in this case, delta positive charges. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.